The ozone layer is in a part of the atmosphere called the stratosphere, which is between about 15 to 30 kilometers above the Earth's surface. About 90% of the ozone in the atmosphere is in the ozone layer. It is a broad peak in higher ozone concentrations from about 2 parts per million to about 8 parts per million. This is much higher than the average ozone concentration in the atmosphere as a whole, which is only 0.3 parts per million. This peak exists because both oxygen and strong UV radiation are required to form ozone. At higher levels in the atmosphere, the air is less dense and therefore there is less oxygen to be converted into ozone. However, less UV radiation reaches lower levels in the atmosphere. Therefore, the location of the ozone layer is a balance between these two features. The ozone layer absorbs most of the UV radiation that reaches the Earth from the Sun. This stops harmful radiation from reaching the Earth's surface and so protects human health and the environment. There is a continual reaction cycle in the stratosphere that converts oxygen into ozone and ozone into oxygen. This reaction cycle is called the Chapman cycle and is named after the person that discovered it. Oxygen is normally bonded to itself to form O2. However, this strong bond can be broken by short wavelength ultraviolet radiation. The oxygen molecule absorbs the radiation and the two oxygen atoms break apart. One of these atomic oxygens can then combine with another unbroken oxygen molecule to form ozone, which is just 3 oxygen atoms bonded together. Another molecule needs to be involved in this reaction to absorb the excess energy that is released during the reaction. This molecule isn't created or destroyed in the reaction and can be any molecule, but usually in the atmosphere is another oxygen or nitrogen. Ozone itself is also broken down by UV radiation. The ozone absorbs short wavelength ultraviolet radiation, and this then reforms the oxygen molecule and the atomic oxygen, and the reaction cycle can then begin again. However, the Chapman cycle on its own is not enough to explain the ozone concentrations in the atmosphere. If these were the only reactions taking place, we would have 5 times more ozone in the stratosphere. This is because there are actually more reactions that lead to the loss of ozone. These other reactions involve free radical catalysts, such as nitric oxide, nitrous oxide, hydroxyl, atomic chlorine, and atomic bromine. Free radicals have an unpaired electron, and this makes them highly reactive. They are represented in these equations by X. The first equations, when combined, form the final equation. And you can see from these equations that ozone molecules are destroyed. You can also see that the free radical is not destroyed in the reaction, and this means it can go on to take part in thousands more reactions and destroy a huge amount of ozone. Now, the stratosphere has a large overturning circulation called the Meridional circulation. It is also sometimes called the Brewer-Dobson circulation, after the 2 people who discovered it. The circulation causes air to rise in the troposphere and enter the stratosphere in the tropics. The air then ascends and slowly moves polewards and then descends in the North Pole and the South Pole. This is a very slow-moving circulation, and transportation takes place on the order of years. As ozone-poor air in the troposphere is transported upwards into the stratosphere in the tropics, it is exposed to sunlight overhead, which breaks down the oxygen and forms ozone. Because of this process, ozone is mostly formed in the tropics. This air is then transported to the mid-latitudes and the poles. This leads to a build-up of ozone in the North and South Pole, and so under natural conditions there is actually higher ozone concentrations at the poles than in the tropics, even though ozone is mostly made in the tropics. The strength of this transport varies seasonally and is strongest in the wintertime and springtime in each hemisphere. This leads to a build-up of ozone and the highest ozone concentrations in the spring in each hemisphere. This polewards transport is much weaker in the summer and autumn. Also, during the summer in the polar regions, there is continuous daylight and therefore continuous breakdown of ozone from solar radiation. This causes ozone to decrease gradually towards its lowest values in autumn. Then this seasonal cycle begins again. This is what the ozone layer is naturally like without human interference.